All right, so here we're going to talk about conservation of energy. This is going to be a big portion, at least of the calculation parts of homework assignments, because this is where you often will get this is where all the questions come from, right? And so the first thing is that mechanical energy, okay, is the sum of all of the potential and kinetic energies on an object. So we write that by saying E, right, is simply K plus UG plus US, okay? So remember, it's the sum of all potential energies and kinetic energy. And the one potential energy that a lot of students will forget is the spring, okay? So remember, what we classify as any conservative force will do work or has a potential energy associated with it, okay? Now, in an ideal system, which means no friction, energy is transferred, right, from potential energy to kinetic energy and vice versa. But the sum is always constant. Okay, so this mechanical energy, regardless of where you are, as long as it's essentially like an isolated system and you don't have to worry about anything coming in or out, that total energy will be constant. So what does that mean? It means that the total energy is conserved. Right, so the mechanical energy before actions equals mechanical energy after actions, okay? Now, in this form of constant energy, the focus is on what we call conservative forces, right? So gravity is a conservative force. Hooke's law or spring force is a conservative force. So a conservative force is a force with a property that the total work done in moving a particle between 2 points is independent of the path taken, okay? Now, a non-conservative force, right, on the flip side of that, okay, is one for which work depends on the path taken, all right? And for us, the big non-conservative force is friction, right? And what happens is friction generates heat, or what we call thermal energy. Right, and that's what leaves systems, right? And sometimes you hear the term dissipative. So dissipative. I don't think I spelled that right. So the dissipative force. So non-conservative is a dissipative force. By saying dissipative, you just get the understanding that if it's dissipating, it's taking away. Okay. So now we can change up the formula a little bit, where we say conservation energy says that the total energy before equals the total energy after, okay? But that translates to be your kinetic energy initial plus your gravitational potential energy initial plus your initial spring potential energy plus the work done by non-conservative forces is going to equal your final. Right? So you're going to be your kinetic final plus your UG final plus your US final. Now, this work done by non-conservative forces, if there's no friction involved, you don't have to write this. But really what happens is it does fit in over here, but as a subtraction, okay? Because on the after side, if I write it, with the taking away what's in the box and putting over here what's in the blue, you can see that it takes away from the energy in the end, okay? And so work sub NC is the work done by non-conservative force. If it's friction, then you're going to use the work formula to determine how much work was done by friction. So remember, work is force times distance, but in this case, the work done would be your frictional force, which is mu times Fn, which typically is mu mg, right, times distance, okay? So what you would do is take this and plug it in there, okay? Or you can plug it in here if you want, okay? And that would be the amount of work done by the non-conservative force, all right? Now, here's the process of solving conservation energy problems, right? So step one, so identify the question as a conservation energy problem. Then you're going to write down the conservation of energy equation and identify your 0 point. This is for U sub G, right? And that's important to do because if you look at, so it's helpful to identify the starting and end points. Sometimes there may be another point in between the points you're trying to solve for, and you can just simply skip that point. And you'll see, I'll show you that here in a second on an example problem. All right, step two, cancel out anything that is not in the problem. So for example, if it doesn't involve springs, anything with an S, you can cancel out, right? If there's no friction or there's no non-conservative force, you can cancel out W and C, okay? And then you're gonna cancel out any values that are not needed, right? And so I guess I forgot to put in here, you really in between steps 2 and 3, you're gonna substitute the equations. Right, so if I have, kinetic energy left over and I have potential or gravitational potential energy left over, we're going to substitute those equations in and then go to step 3 where it says cancel out any values that aren't needed or aren't there. Okay, sorry about all the grammatical mistakes. For example, a lot of times I don't give you mass in some of these questions. It's because you don't need it, because it cancels out. The only time that mass actually will stay in a problem is if you do have spring, okay? Because the spring doesn't have a mass factor. And then finally, you're going to solve algebraically for what you're looking for, and then substitute in the values to get your answer. Now, one thing to note, I'm going to highlight this, is that you may have to do it multiple times, okay? Because it may be a part A, B, C. It may be something where you can't skip the point in between or something like that. But again, the best thing about conservation energy problems is just let's do them to see how this works. Okay. So here's the question: you launch a 4-kilogram object directly up from the ground with 40 meters per second. What maximum height does the object reach? And now this actually says use conservation energy to solve the problem, because we've done something like this with kinematics. Okay, you can solve this using kinematics, but you'll actually see the equation works out to be the same. All right, so the first thing we're going to do is we're going to write down our equation, our conservation energy equation. So Ki plus UGI plus USI plus work done by non-conservative forces equals our finals. So Kf plus UGF plus USF. Right? And remember, the work done by non-conservative forces pops up on one side. If it pops on the before side, it's added. If it pops up on the after side, it's subtracted. Okay. Now we're going to start crossing out things that that aren't present. So we don't have a spring, right? So that can go away. We don't have any friction or air resistance or anything like that. So that can go away, right? That's 0. This is 0. Okay. So here, if you want to say, here's our physical picture, right? So we're launching up from the ground. So we'll call the ground h equals 0, right? And up here, the height we're looking for, right? Well, you have to remember, it's going to stop at the top, right? So it's going to allow us to cancel out 2 more things, right? So since we're launching from the 0, the initial potential energy gravitational will be 0. And then because we're going up to a, no velocity, the final kinetic energy will be 0. And so what do I have left? Ki. So out of all that mess, there's only 2 things left. Ki equals UGF. Right? And so now we plug in our equations. So we have 1/2 mv squared equals mgh. Right? And note that they do give you the mass of the ball, right? But you don't need it, because look what happens. The masses cancel out, and I just solve this for v, right? Multiply by 2, and then take the square root. This is the square root of 2gh. Now, if we use kinematics, we would have gotten the same equation, but we would have like 2 times a times d or something like that. So now we just plug in our values. 2 times 10 times, oh, I'm sorry, we're looking for h. Because a lot of times in the equation, you're looking for the final velocity. I apologize. So we're looking for h. And so we're at, let's see, we had 1/2 mv squared equals mgh, right? Again, masses will cancel, and so all we're going to do is divide this by g. So h equals v squared over 2g. And so it's going to be 40 squared over 2 times 10. Again, we'll just use 10 for simplicity, which means it's going to go a height of 80 meters. Okay. Okay, so in our next question, we have a 6 kilogram object thrown down at a height of 20 meters. If the object reaches the ground with 30 meters per second, what initial speed did you throw it with? Again, guys, this is all process driven. Okay? So we're gonna use our process, right? So we're gonna write down our conservation of energy, and so Ki plus UGI plus USI plus work done by non-conservative forces equals K final plus U final, UG final plus US final. Okay, and so we're gonna, whatever we don't have, we're gonna cross out. So for example, we don't have springs, so that's gonna go away. Springs is gonna, right? We don't have any non-conservative force, right? There's no air resistance, there's no friction. If it doesn't mention it, always just make that assumption, okay? And so now we need to decide, we're gonna call the ground 0 or we're gonna call where we release this from 0. You can do whichever one you want, okay? So let's call the ground 0. So that means our final potential energy is 0, right? And so now we're going to, what do we have left over? We have Ki plus UGI equals Kf. Okay, and what we're looking for is contained in Ki, right? So the 1/2 mv squared. So we're going to do 1/2 mv0 squared plus mgh equals 1/2 mv final squared. All right, and so we're going to solve this equation for v0 squared. One thing to note, same object as it's traveling, right? So you can get rid of that, you can get rid of the mass. If I multiply all this by 2, I get rid of the fraction, so I get VO squared plus 2GH equals V squared. And then I'm going to subtract 2GH, right? And so it's going to leave me with V0 squared equals V squared minus 2GH. And then the last thing to do is to take the square root. So square root of V squared minus 2GH. And now I can plug in numbers. I'm going to say V0 equals the square root of final velocity 30 squared, right, minus 2 times 10 times 20. Now we're going to take the square root of that. And what speed did we throw it down with? Well, we threw it down with a speed of 22.4 meters per second. Okay. So one thing to note, this is essentially another free fall question, just like the previous example. It does, right? It gains speed, right? So it starts at 22.4, it ends at 30 meters per second. So you can tell that it does gain speed as it travels down. Okay. All right, next one. A block of unknown mass is sliding on a flat surface with 30 meters per second. When it enters a long rough patch, the coefficient of friction between the block and the rough patch is 0.6. Calculate the block's stopping distance. Okay, and so here's one where we do have a non-conservative force. But again, go through the process, right? So we have Ki plus UGI plus USI plus WNC, right? The work done by non-conservative forces is going to be equal to Kf plus UGF plus USF, okay? Now, cancel out things that we don't have, right, or we don't need. So note that there's no height difference. We're on the same table. The object's not changing its height, so your potential energy is going to be 0. We don't have springs, right? So your US's are going to be 0. Okay. Now, there's one other thing that we can cancel out. It's our final kinetic energy because it comes to a stop, right? It talks about calculate the stopping distance, right? So what's left? Ki plus work done by non-conservative force equals 0. Okay? And so what we're looking for is something contained in the work done by non-conservative forces. So we got 1/2 mv squared plus fd, right, equals 0. Okay? And this D is what we're looking for. And so if we kind of want to go through and do the steps now, you got 1/2 mv squared equals negative FD. Okay, and so then you've got 1/2 mv squared. Well, the force that's stopping is friction, so you get negative mu mg v, right? And so then we're going to kind of go through, so we cancel out m's, right? If I'm looking for d, I'm going to just simply divide by negative mu g, and so I'm going to end up with negative v squared over 2 mu g, okay? And so what you can actually do is, just say, okay, this is still moving forward, right? And so we can just call this a positive. And so what happens is now I can plug in numbers. So it starts at 30. You got 2 times, and the coefficient of friction is 0.6 times 10, right? And so it's going to be, in fact, the reason why this would be, this will actually be a positive because the work done here would be a negative, right? Because it's going to subtract out. And so you're going to find that it would take 75 meters for this block to stop, okay? And so that was an example where we had a non-conservative force doing some work, okay? All right, next question, the last one here in conservation energy is going to talk about a skater dude, right? So you have a 70 kilogram skater dude rides on a half pipe, which is a perfect semicircle of radius 3 meters as shown, right? And so what they're saying is that, right, this is 3 meters. He's starting at 3 meters and going down and coming back up. Then we're going to calculate the speed at different points. We're going to calculate it at point B, point C, and point D, right? All right, so to find B, right, we're gonna do, so find the speed at B. We're gonna do our process, KI plus UGI plus USF, or USI, sorry, plus WNC equals KF plus UGF plus USF, right? So there's our conservation energy. We're going to cancel out things that we don't have. So we don't have springs, right? So the S's can go away. We don't have a non-conservative force, so that can go away. We're going to call the ground 0. So HE 0 is going to be at the ground. So that means at point B, it's at it's at potential energy is 0. And then it's starting from rest at point A, so your KI will be 0. So essentially what's left over, UGI equals KF, right? And we're looking for something in KF. So you have MGH equals 1/2 MV squared, okay? Again, do you really need to know what the mass is? No, because it just cancels out. And so you're going to find that the speed is going to be the square root of 2GH. And so you get the square root of 2 times 10 times 3. And at point B, the skater is moving at 7.75 meters per second. Okay? All right. B and C, you can do more conceptually. Okay? All right, so at point C, one thing I want to note, A to C means there's no height difference. So if you go back to your equation, your UGI and UGF would cancel out, right? Because they're the same height, okay? Your KI it would cancel out. There's no springs, there's no work done by non-conservative forces. So the only thing you have left over would be 0 on the left-hand side equals 1/2 MV squared. Well, how do you produce 0 energy, right, with a speed? Well, there would be no speed at point C. So at C, right, the V would be 0 meters per second, right? And the conceptual idea is that it's whatever you have at A, okay, that's the amount of energy you have to carry. And note, so the point A sets the total energy, right? And so that's just, if it's starting from rest, that's just MGH, okay? And if I come over to C, H is the same thing, right? And so that, what does that mean? That it actually stop at point C. Okay. All right. So before I mentioned the part at point C or point D, you would have to do it kind of conceptually. You actually could work this out, right? And so if I do part, sorry, I was panning, not panning. So part C, again, we're going to start with, right, our Ki. So if we start with our initial our kinetic, our total energy, which is what it's already written here, what happens is the equation breaks down to be K initial plus UG initial equals UG final. Okay, because at D it's going to stop. Okay, and so we're going to solve this for our initial velocity. And now you do have to recognize that there is going to be a height difference. Okay, and so masses cancel. And so the formula breaks down to be V0 equals the square root of 2g times the difference in height. So the final minus the initial height. Okay, and so you're going to say V0 equals the square root of 2 times 10 times 5, because it's going to be 2 meters above point C. C is at 3 meters, right? And D is 2 meters above that, and A is at 3 meters. And so you're going to find that the velocity will end up. So to get to point D, we would have to start with a minimum velocity of 6.32 meters per second to get to point D. Now, if the question talks about you start from rest at A, what would be the speed at D? You would never get there again, because position A sets the energy, and note that you can't go any higher than your initial energy, right? So to get to D, you would have to gain energy to go up, okay? But this says we're finding the speed at A to reach point D, right, which is 2 meters above point C, okay? And so we have pie charts and work, or excuse me, power left to do, okay?